Okay, so partial derivatives, what we're going to do is we're going to look at some examples in the book. And I think once you see some examples, I think partial derivatives, it's going to be helpful that you have some time to practice. So I want to just look at some examples and see if you have questions, and then hopefully I'll be able to give you some time to practice work on that assignment. And then of course I'm here if you have questions. So let me just kind of go through here so partial derivatives. All right. So what is a partial derivative? Well, it's a rate. Okay, and the formal definition of a partial derivative is right here. Okay, that's the formal definition of partial derivatives. So if you have a function of two variables, a function of x and y, well, you're used to, well, let me just see here. Hold on. Do these definitions of partial derivatives remind you of the definition of a regular derivative? They're similar, aren't they? But you see, you have a function of two variables. So, see, if you're looking for a rate of change, how does the function change with respect to a variable? You have to pick one variable. Okay, so you can study how your function f of x, y, how does your surface change as you let x vary, or how does your surface change as you let y vary? Those are partial derivatives. So the partial derivative of f with respect to x is the top limit. You're holding y constant, and you're letting x vary. Well, you're studying how, I want to say this the right way. You're studying how, for a partial derivative of f with respect to x, you hold the y constant and find the slope of the tangent line with respect to x. For the partial derivative with respect to y, you hold the x constant and you're finding the slope of the tangent line with respect to y. That's really geometrically what you're doing. So we can go to a very nice example here, example 2. And I'm just going to go right there to the example. Oh, by the way, these are notations for partial derivatives. These are all different notations for partial derivatives. And I know you haven't, being you're in calculus, you're multivariable calculus, you haven't actually computed partial derivatives yet. But how many have seen symbols like these somewhere? Okay, Eric's seen them. So, just like, and Marvelous has seen them, you have Newton notation and you have Leibniz notation. Absolutely, Eric. That's right. Not uncommon in physics. Okay, so let's see, really, let's get a geometric feel for these partial derivatives. Okay, so in example one here, you have a function of x and y, which equals x cubed plus x squared y cubed minus 2y squared. And you want to evaluate the function. You want to evaluate these two partial derivatives. The partial derivative of f with respect to x at 2, 1, and the partial derivative of y with partial derivative, I'm sorry, let me say this again. You want to evaluate the partial derivative of the function with respect to x at 2, 1, And then you want to evaluate the partial derivative of f with respect to y at 2, 1. So look at how they compute the partial derivative of the function with respect to x. They hold the y constant. They hold the y constant. Let me just see here. Let me go to the whiteboard. I actually didn't want to. Let me go to the whiteboard and just write this function down. So f of xy is equal to, it was x cubed. Okay, hold on here. X cubed plus x squared times y cubed minus 2y squared. Okay, and you want to find the partial derivative of the function with respect to x. So that means you're going to hold the y variable constant. You're going to hold the y variable constant and differentiate this function with respect to x. So, of course, the derivative of x cubed is 3x squared. Okay, and y cubed is treated as a constant, so that just stays there. But the derivative of x squared is 2x. And then the derivative of 2y squared is just 0. Because you're treating the y like a constant. And so that's going to get you then 2x times y cubed plus 3x squared. Okay? You've just seen your first partial derivative. Are there any questions? All right. Well, let's look at the partial derivative of this function with respect to y. So what I'm doing is example 1 in the book. I'm just doing like a portion of it because I think it helps to talk about it using the whiteboard. So now for this partial derivative, the partial derivative of the function with respect to y, what variable is held constant? The x. Good. You hold the x constant. So then I'm going to have something plus something plus something. Okay, so I'm looking here at these three functions. All right, if I hold the x constant, what's the derivative of x cubed? Good, 0. If I hold the x constant, what's the derivative of x squared y cubed? Good. It's just going to be, well, It's going to be x squared, because that's held constant, times 3y squared. Okay, and then what's the derivative of negative 2y cubed? If I negative 4y. Good, you're getting a good feel for this. So this is going to equal then 3x squared times y squared minus 4 times y. Okay. Okay, and those, are there any questions on those partial derivatives? All right. On that note, let me get back to the book then. That's not back to the book. Hold on. Okay, so then naturally you can evaluate the partial derivatives at different points to get different answers. And that's what they do in example 1. Are there any questions on that? So like you know, they wanted you to evaluate the partial derivatives at the point 2, 1, and you would get, in this case, partial derivative of f with respect to x at 2, 1 is 16, and the partial with respect to y at 2, 1 is 8. Okay. Well, if you're good with that, let's move on. Let's look at another example. Interpretations of partial derivatives. So I think it's easiest to go right to an example here. So in example 2, they want you, they tell you that you have this function, f of xy, equals 4 minus x squared minus 2y squared. And they want you to evaluate those two partial derivatives at the point 1, 1 and interpret the numbers as slopes. Okay. So I don't think it's too hard to see that these two partial derivatives are as they are. And when you evaluate the partial derivatives, the partial of f with respect to x at 1, 1 is negative 2. And the partial derivative of f with respect to y at 1, 1 is negative 4. Are there any questions on what you're seeing right there? Okay, Eric's good. Is anybody uncomfortable? All right, all right. Who's good so far? Maybe if I have a few thumbs up, I'll feel confident moving forward. All right, Robin's good, and Marvelous is good. Jamal and Christopher and Ryan, okay, all right. Well, so what this in example 2, this function 4 minus x squared minus 2y squared. What is that? What is that surface? What is that surface? Is it Is it a cone? Is it a paraboloid? Is it a sphere? Yeah, it is a paraboloid. And let me ask you, does the paraboloid go up? That's right, Robin. Does this paraboloid, what's the highest point on this paraboloid in example 2? What's the highest point? That's right, Ryan. That's right, Eric. 4. Does the paraboloid open upward from 4 or downward from 4? Good. It goes downward. So, in our minds, we picturing this paraboloid opening downwards. Okay, and these two partial derivatives, well, derivative is traditionally you've learned that a derivative is a slope of a what? The derivative is a slope of a what kind of line? Good. That's right, Eric. That's right, Diadath. A tangent line. Okay, so slope of a tangent line at a point on the surface. On the surface. Because this function f of xy is a surface. So okay, no problem. Well, all right. So 1, 1 is in. Of course, it's a point in the xy plane, but then we look at the surface above the point 1, 1. And let's see here. We have the partial derivative of f with respect to x at 1, 1 is -2. The partial derivative of f with respect to y at 1, 1 is -4. So let's look at a picture here. Those must be slopes of some tangent lines. Would the -2 be a slope of a tangent line? So let's look at that first slope there, -2. Would that -2 be the slope of a tangent line going in the x direction or the y direction? Why? That's right, Ryan. X direction. Why would you say the x direction?
Because it's from the derivative with respect to x.
Perfect. And the derivative, the -4, what direction would that tangent line be going in? Good, Ryan. Good, Diadath. The y direction. Good, Jamal. So you already have an intuitive feel for this. You already have an intuitive feel for this. And if we go down and look at the picture here, what they've done is they've drawn in figure 2, when at the point 1, 1, 1, that's when x is 1 and y is 1. Of course, z equals 1 then for those x and y values. They've drawn a tangent line. So what's the slope of this tangent line that you see in figure 2? The tangent line to the surface. Tangent line to that point on the surface. What would the slope of that tangent line equal? Well, okay, think about the derivatives we just computed. Is this tangent line, is it pointing in the x direction? I mean, is it parallel to the x-axis or the y-axis, that tangent line in figure 2? Parallel to the x-axis. So the slope of the tangent line is with respect to the x-axis. What was the value? What was the value of the partial derivative of f with respect to x? Do you remember? It equaled -2. That's right. Does that tangent line have a negative slope with respect to the positive x direction? Absolutely, the tangent line is going down with respect to the positive x direction. So it has a slope, and a negative slope, and the slope is -2. Okay. On the other hand, let's look at figure 3. Here's our paraboloid again, and we have a tangent line at the point 1, 1, 1. But that tangent line is parallel to what axis? Hold on, good, parallel to the y-axis. All right, what was the partial derivative of the function with respect to y at 1, 1? Good, Diadath, -4. Is that tangent line, as with respect to the positive y-axis, is that tangent line, is it going up or down? Going down. Good, good, good. And what's the slope? What's the slope of that tangent line? -4. Good, Jamal. Good. Okay, okay. So far, I mean, are there any questions so far? How many find this helpful to have a geometric field for these partial derivatives? All right, excellent, excellent, excellent. All right, good. And it's kind of nice to discuss it. You know, it's one of these things where we want to look at pictures and discuss. Well, let's go a little further here. Let's go a little further here. Example 3, we have a function. Okay, we have a function of x and y, and we want to calculate the partial derivative of f with respect to x and the partial derivative of f with respect to y. Okay, this is a little bit more interesting function, right? So let's see here. Let's take a look at these partial derivatives. Let's look at the first. Well, when I highlight it, I have to highlight both, unfortunately. But the partial derivative of f with respect to x on the first line there, it equals the cosine of x over 1 plus y times the partial derivative with respect to x of x over 1 plus y. Hey, what rule seems to be being used here in this example? Good, Eric. The chain rule. The chain rule. When you take the derivative of the sine, you get the cosine, but then you have to differentiate the angle x over 1 plus y with respect to x. But you're holding the x constant, so the derivative of x over 1 plus y with respect to x, the partial derivative, is just 1 over x plus 1 over 1 plus y. And similarly, for the partial of f with respect to y on the second line, well, you hold the x constant, and you're going to get 1 over 1 plus y squared for that second factor. Now, what rule did they use there? In other words, maybe what I'll do, maybe I'll write it out here. Hold on. Let me go to the whiteboard. Hold on. So, hold on here. You have the partial derivative with respect to y of x over 1 plus y. I have a quotient here. So could I use the quotient rule? Sure. Okay, well, let me set up the quotient rule then. Okay, so we know how to set up the quotient rule. Okay, what's going to go here? Good, 1 plus y. Okay, what's going to go here? So you're differentiating with respect to y. That means you hold the x constant, right? Hold the x constant. Treat it like a constant. Okay, so if you do that, well, people do that. Let me show you how I do it. I'm gonna put 0 here, 1 plus y. Okay, minus 1 times x. So the derivative of x was 0 times 1 plus y minus the derivative of 1 plus y, which is 1 times x. And so this means you'll get negative x over 1 plus y quantity squared. Okay. So far, so good? It takes a little while to get used to it, but you will get used to it. All right, thank you, Deodath. Thank you. And so now if I go back to the book, that second part there in example 3 should hopefully make sense. Partial derivatives give you hold on, wait, there was a chat thing here. Eric, is the book wrong with the derivative with respect to x? No, no. No, it's okay. So you're looking at example 3, Eric? Yeah, well, the derivative, so the function was the sine of x plus y. The derivative of sine is cosine. So hold on here. So this is your function right here. That's what you're differentiating. Okay, no problem, no problem. All right, very good, very good. Are there any other good questions? Ah, okay, okay. No problem. All right, well, let me show you a few other things here while we're here. Okay, let me show you a few. So you can do implicit differentiation as well. Example 4. I'm going to let you look at that. Okay. I'll let you look at that. Let me keep going here. You can have functions of more than 2 variables. You can have functions of 3 variables or 4 variables. And when you do that, of course, you'll have more partial derivatives. Okay, I think you'll be fine on that. I want to get to this next part here. Higher derivatives. Higher derivatives. Oh my goodness. Well, you know, in calculus, we don't stop at 1 derivative, right? We stop, I mean, in calculus, the second derivative of a function with respect to x would represent what geometrically? The second derivative of a function with respect to x. So first derivative is slope of a tangent line. Okay. Tells you if the function's increasing or decreasing. Second derivative, I'm now just talking about an f of x. Ah, that's what. And I appreciate all responses. Concavity. That's right, Robin. Concavity. Second derivative is concavity. Well, for higher derivatives, okay, if you have a function of x and y, how many second partial derivatives are there? How many second partial derivatives are there? Yeah, there are 4. And each one of them has a geometric interpretation, by the way. If you have f sub xx, that stands for concavity in the x direction. Concave up, concave down in the x direction. Okay, that's what, hold on here, let me go. This, man, won't let me see, can I just do one at a time? Nope. Okay, well, so in the first line here, and I think you can see it pretty well, f sub xx, that's Newton's notation for second derivative of f with respect to x, second partial derivative of x with respect to x. That would be concavity in the x direction. The last line, f sub y, that's the second partial derivative of f with respect to y. That would be concavity with respect to the y-axis in the y direction. And you'll have a few surfaces where you'll actually practice that. And then then you have the mixed partial derivatives, okay, on the second and third lines, okay. But let's just look at example 6, okay, and then I want to set you off to work a little bit. I think practice is going to be very nice for you here if we can do some practice in class. So let me see here, one moment. Okay, so example 6 is find the second partial derivatives of this function. So first, you have to find the 2 first partial derivatives. You can't get the second partial derivatives until you've done the first partial derivatives. Okay. Okay, these are going to be your all your second partial derivatives. Are there any? Just look at them and let me know if there are any questions. Do you see anything interesting?
The partial derivatives of x and y in either way, order is the same.
That's very good, Ryan, and that's correct. We call those the mixed partial derivatives, but they are the same, and that's due to Clairaut's theorem. The mixed partial derivatives, f sub xy and f sub yx, are going to be always equal. That's no accident, and that's proven in the textbook. Okay, pretty cool stuff. Are there any questions on how they got those answers? All right. Well, let me show you one more thing here. Let's see here. I want to show you one more thing. You can, by the way, go even higher partial derivatives. Okay. Now you might wonder, well, gee, Dr. Judy, you know, beyond concavity, why would we need beyond the second derivative? We know second derivative is used for concavity, concave up, concave down. Why would you need higher order derivatives? Well, how many remember Taylor polynomials from Calculus 2? Taylor polynomials. Okay, Robin remembers them. Diodath remembers them. Well, don't you have Taylor polynomials where you go out to the third derivative, fourth derivative, fifth derivative, right? Taylor polynomials, you can go out to, if you want to approximate a function, okay, the more the terms of the approximating polynomial are based on derivatives, and the more terms you take, the better the approximation will be. If you're trying to approximate a complicated function with the Taylor polynomial, the more terms you take, the more terms you take in the polynomial, the better the polynomial approximates the function over a wider range of x values. Well, there's an equivalent here for approximating a surface with a Taylor polynomial of multiple variables. And you know, I mean, that can get pretty messy if you beyond the first partial derivatives. But there is an application of that. Actually, in graduate school, I studied that a little bit. It came up in my research work. Now, one more thing here. I want to give you a little time to work here, and then a little time, but there is hold on here, I wanted to show you. Maybe I've got to go to the next page. Let me see, it's comes after example 7. Right. Okay, very good. Yeah, partial differential equations. Okay, so partial differential equations will come up in engineering. They will come up. Has anybody heard of the wave equation? Has anybody seen this? I mean, I guess probably not yet. That's why you need, how many need this class for their physics class, upcoming physics class? How many need the Math 280 or are doing it like simultaneously? Yeah, okay, and Eric has seen the wave equation. Yeah, second partial derivatives. Okay, so very, very, very important material that you're learning here. Are there any questions? Okay, I'll stop the recording.